In this chapter, we're going to be talking a lot about alkenes, so that's why I wanted to review some of the concepts that we already know and expand it to new ones. So as you know, alkenes are hydrocarbons, meaning that they are only composed by carbons and hydrogens, and they contain double bonds. So each carbon on the double bond is sp2 hybridized, which means that it's trigonal planar and that the bond's angles are 120 degrees apart. As you know, a double bond is composed by a sigma bond. So if we have a double bond that would look like this, it's composed by a sigma bond right there, and then we'll also have a pi bond composed by these orbitals. Because of that double bond, there's no free rotation around that bond. When you have simply a single bond, just like this one right here, the sigma bond can rotate. But when you have a double bond, that rotation it's not there anymore. So at that point, we can only have a cis double bond or a trans double bond, and we cannot interconvert them now. As you know, because we saw this in class and we've seen it many times, the cis stereoisomer is less stable than the trans stereoisomer. The reason for that is these hydrogens that are right there, they are closer together in the cis than they are on the trans. On the trans form, you see those two hydrogens are no longer touching each other. So that's why the trans is more stable. Now, when we talk about alkenes, there's different ways to classify them. We can call them cis and trans. We can call them E and Z when they have four substituents. And now we're gonna learn another way to classify them. So we can call them monosubstituted, disubstituted, tri, and tetrasubstituted. And that depends on how many R groups are connected to the double bond. When there is only one R, like in this case, it's mono, two R's, di, three R's is going to be tri, four R's is going to be tetra. So remember that these are simple alkenes, they are open, but we can see cases like this disubstituted one where you have two substituents. Another way of thinking about it is how many hydrogens are still connected to the double bond. So if you look at it in the monosubstituted, there are still three, disubstituted two, trisubstituted there is one, and tetrasubstituted there is none. So for example, if you go back to the cycle, if you think about it, there is only one H and two H's, so that means that it's disubstituted, just like this one right here. Or if we look at this one, in this case, it's connected to three R's. You see 1, 2, 3. That means that there is only one H still connected to it. Now, the alkenes, they will become more stable when you have more R's connected to it. So a molecule like this one, where it's not substituted at all, is going to be less stable than a molecule when you have four R's connected to it. Those R's can be the same or they can be different R's. And the reason for that is because sp2 hybridized carbon, like the ones in the alkenes, has more S character, which means that it can accept electron density. So when you have an R connected to that sp2 hybridized carbon, it will be donating electron density, and that sp2 hybridized carbon will be able to accept it. That is not true, or that doesn't happen so much when you have an sp3 hybridized, because an sp3 hybridized doesn't have so much of an S character. So I'm going to say these again because it can be a little challenging. So an sp2 hybridized carbon, just like this one, has more S character. Remember, it has a 33% S characters, whereas a sp3 hybridized will have a 25% character. We learned that way back in the course. Now, Because it has more S character, it has the capacity of accepting more electrons, because remember, an S is spherical and it can accept electrons better. So whenever you have anything that is different from a hydrogen, like an R, when you have electron donating groups, they will be donating to the sp2 hybridize. So those sp2 hybridize can accept electron density. When you have an sp3 hybridize, it cannot accept electron density so well. So that's why the more substituted your alkene is, the more stable it will be. And so this is the general stability trend. The more substituted your alkene is, the more stable it will be. So here we have a monosubstituted versus disubstituted alkenes. So the more substituted your alkene, the more stable it will be. And between the cis and the trans is going to be more stable, because remember that those two H's are far apart, and in here those two H's are way too close in proximity.